Good afternoon, ma'am. This is the continuation of the report of the hyperbolic geometry. We are in the third phase of the report now. We are number three. Now, in this part, this is referred to Ryan and Smart with point-colored disk model. This is from this report is all about and based from the reference of Ryan and Smart. So, now because I can simply put the laptop here, so I might edit this and just put here the PPT. So now let's discuss first the classification of parallels. Now, in their reference, they state that given a line L and a point of P not on L, lines through P fall into three disjoint classes. So three disjoint classes. We have those intersecting L, those diverging from L, or what we call ultra parallels, and exactly two asymptotic limit parallels. Now, based on the wordings that I just said, it's quite hard to understand, but it's actually pretty easy to understand. Now, why not let's uh, draw draw this to mm, ease ease up our understanding. So now, so if we have, imagine if we have a line here, a horizontal line. Okay. Now, having a point here. So in the statement, this is the line L, right? This is the line L, and this is the point P. Now, let's just imagine that this line L is actually a road, and this point P, this point P right here, is actually where you stand beside the road. Now, uh, it is going to be separated by three disjoint classes, right? So first we have what? We have the paths that crosses the road. So we have P crosses L. We have P, you are here and you want to cross the road. So eventually you are going to intersect with the road. So P can intersect L right here. So that's the first disjoint classes. Now, and the second one is what we call the ultra parallel site. So this is the paths that miss the road completely. So in the first disjoint classes, we intersect the road, right? So and from that, the second case is actually the opposite one. It diverges from the road. So you walk in a direction that takes you away from the road. So where is that going? Where's the line going? So correct, going upwards, opposite to the road. It's either going to be here, either going to be here, and either going to here. Not closer to the road, but actually going diverge, divergent to the road. So going farther away. Now, in the third one, we have, again, in the PPT, let's read that. We have and exactly two asymptotic limit parallels. Now, based on my understanding in the English, so it's quite hard to understand that asymptotic limit parallels. Now, let's divert it into an easy understanding. Now, let's just imagine the asymptotic parallels is just exactly two special paths that you walk along the road. Now, you walk in a direction that runs alongside the road. So it's either going to here, you are going to walk beside the road, or either going near the road but not intersecting the road. So you can get closer to closer to closer to closer to the road but not actually stepping on the road. So further example, if this road right here have coals on it, so you can decide the path where cross. You can cross the road. You can cross the road with hot coals, just stepping on the coals, or diverging to the coals. You're not going near that road with course, or just going to a straight line following the road of course. You get closer and closer and closer that you feel the heat from the road because of the course. Now, that is the that is the theorem or the statement according to Smart and Ryan in the classification of parallels. Now, why not let's move on. Let's move on to the AAA congruence theorem. Now, this is the statement right here. Again, I'm going to edit this and it's going to be right here. Okay, the statement is if the three angles of one triangle equal the three angles of another triangles in hyperbolic geometry, then the triangles are congruent. Now, how can we actually see that? Sir, in geometry, in, geom- in Euclidean geometry, if two triangles have the same angles, then they are congruent, right? Regarding to their size. So meaning, um, meaning, if we have a smaller triangle here and a bigger triangle right here, if they have congruent angles towards each other, then they are congruent. This is from the Euclidean geometry. But in our statement right now, based on Ryan and Smart, if in the hyperbolic geometry, so we are in the hyperbolic geometry, right? So what space are we in? In the flat space or the curved space? Correct. We're in the curved space. When we talk about the flat space, we are in the Euclidean geometry. So because this is this is hyperbolic geometry, we are discussing around or on the curved space. So in the regular geometry, if two triangles have the same triangles again, if they have the same triangles, congruent to each other, they might be different in size but the same shape. So this is accepted. This is accepted in the normal Euclidean geometry because we are discussing in the flat space side. So we can say that this triangle is actually bigger shape than his congruent triangle which has a smaller shape, but the two angles actually have congruent angles. So in hyperbolic geometry, if two triangles have the same three angles, then this can only explain one thing. They are correct. They are identical to each other. It's not regarding to their size, but actually we can tell that the smaller triangle is just the same as the bigger triangle because we are discussing in the curved space light. So it's the perspective view. If you are looking here, you can see or you can say that you cannot say that this triangle right here is actually bigger than this triangle because we are in the curved space. In flat space, we are just going horizontal, flat surfaces. But in hyperbolic geometry, we are curving the space. We in hyperbolic geometry, we see this as a curved space. The curved space right here. So meaning, we can see that in this view in the curved space, we can actually say that if two triangles have the same three angles, then they are congruent to each other and they are identical. So we can say that the one triangle is bigger than the other triangle. They can only be one triangle that have that size. It have a fixed position. So meaning the two triangles have actually the same size and shape. So this small triangle right here is actually the same as the bigger triangle right here because we are discussing again in the hyperbolic space. Nevertheless, that if we discuss this in the Euclidean geometry, uh, which we are in the flat space, then we can actually say that this bigger triangle right here is actually bigger than the smaller one. So, so again, in the hyperbolic geometry, the curve is space, and if two triangles have congruent three angles, then we can say that the two triangles are identical and congruent regarding to the size. So they are actually the same size and triangle. So now we are here in the Poincaré-Desch model. So I am very excited to discuss and present the Poincaré-Desch model to you guys. Now, first things first, what is the definition of Poincaré-Desch model? So, a Poincaré-Desch model, let's just have it like a magic map or a magic circle right here. Now, this magical map contains the hyperbolic geometry inside of this map right here, a circle. Now, the boundary, which is what we can see, the edge of the circle, represents forever far away. So, meaning it's infinitely such as. So you can actually get to there, but you can actually get closer and closer to that thing, but you can actually get to the edge of the point of the desk model. So it's most likely like the horizon that you can see outside, but you can actually never reach it. Like the universe expanding every second right now. Now, the inside of the circle right here, the distances get such as getting closer to the edge right here that it's actually from one, the distance one is actually when you get closer to the edge right here, it's actually getting infinitely large. It infinitely stretched. So that's why you can actually get to the boundary of that circle. So now let's go on to the first theorem of Poincaré-Desch model. So we have theorem 1. Again, I'm going to fix it right here. We have the conformal property. So what is conformal property? So in the Poincaré-Desch model, the angle between two intersecting hyperbolic lines equals the Euclidean angle between their circular arc representatives at the point of intersection. Now, in the Poincaré-Desch model, the circle where we draw the hyperbolic geometry, the curved lines, we have the curved lines right here, the curved lines that represent hyperbolic lines may look strange, right? Because we are in the curved space, right? But there's one thing that stays perfectly the same. What? The lines, the angles, the points, what? Guess. Yes, you guessed correctly. It's actually the angles. If you use actually a regular protractor to measure the angle where two curved lines intersects or lines meet, you get the actual hyperbolic angle or the same angle. Imagine you're looking at what? You're looking at this image right here. Uh, let's just imagine that this is a distorted photograph right here. It's not just far north side, far northeast of this, where everything is stretched and curved. But in this photo right here, the corners and angles, the angles right here, still looks perfectly correct. Like if two no, if two walls meets at 90 degrees in real life, they still look perfect. They still look the same, like 90 degrees, in this distorted photo. So to further understand this explanation, the line. Let's just draw this inside the Poincaré-Desch model. Right? So if we have two curved lines that meet at a certain point, let's have here two curved lines. Now, if we use an actual protractor like this, I don't have a protractor now. It's it's the true geometric angle right there. So meaning uh, meaning even though the lines look curved and the light looks curved, the angle preserved perfectly. The angles preserved perfectly, right? So in the flat surface, in the Euclidean geometry, it's going to be like this. And it's actually the same as like this one, right? Because in the hyperbolic space, we are in the curved surfaces, and this is actually in the flat surfaces. So from the Euclidean geometry to the hyperbolic geometry, the angles stays the same. So that's why that's why uh, it is called again it is called the conformal model because it preserves the preserves the angles. It distorts lengths, but it's actually keeping the true angles. So that's why it's called conformal model. So now let's move on to the theorem 2, which we discussed the distance formula. So again, I'm going just to pause it right here. So again, if we write down the distance formula, we have the distance of the point 1 and 2 is actually equals to cos to the power of negative 1. I'm not going to write that anymore because you can actually see that on here, from here. So now let's discuss it. Now, how do we explain the distance formula in the Poincare model? So now it's actually true. Do you agree that the formula is actually scary looping because we don't understand it, what the points are? But it's just actually telling us that let's discuss this. Let's as a drawing. Now it's actually telling us that in the center, the distance in the center, not on the edge, is actually normal. It's just normal distances. But as you move towards the edge, it stretches further and further away. So, for example, if from the center to the middle part of the Poincare model took what 10 steps, but if you are going to the from the middle part of the Poincare model to near the edge, it actually taking you 10,000 steps. It's the formula is just telling you how it looks like in the distances in the flat surface and the Poincare model that have that have the hyperbolic geometry identities. So so uh, okay, z1 and the point 1 of point 2 squared is actually how far apart they look like on the paper or on the board. So if this is z1 and this is z2, z1 minus z2 squared is actually means how far they are from the edge. So that is the numerator, and the 2 right there represents how many points they are. So now let's move on to 1 minus z 1 minus point 1 squared and 1 minus z point 2 squared. This tells us how close the points is on the edge of the circle. Save na ko. Now, okay, misinterpretation right there. So actually, z1 minus z2 is actually the distance between the point 1 and the point 2 right there. and the 1 minus z1 squared and 1 minus z squared, z sub 2 squared is actually the distances from the point to the edge, to near the edge. So I guess this explains the formula, right? So uh, I'm just going to link this formula in a real life example. So imagine if you are what in your you are in museums, right? So you do pictures right there, but imagine walking through the halls of an museum empty museum. It feels all right, normal, right? uh, and it's just like this. The ends of the circle is actually the museum. And right here, you are in the halls. You walk normally, perfectly fine. You move quick. But imagine walking through the same distance near near the exit now. Near the exit now. This is the exit of the museum. Now you are going to the exit time at the closing time. Closing time. So uh, since it's closing time, many tourists actually run forward to the exit to exit the museum, right? So the crowds get thicker and thicker, so you move slower. So it's actually mirroring the distance of Poincaré model right there. So uh, if you go near the exit, it's going to be crowded and takes you time. But in the Poincaré model, you can actually exit or touch the exit of the boundary because it's going to be crowded and crowded and crowded until it stretches infinitely and you can actually get to the exit point. So the formula is just representing that statement right there on what I said. Now let's move on to the third theorem, or what we call the isometries as Mobius transformation. So in the theorem, every isometry of the pointer, this model, can be expressed as a Mobius transformation the formula right here, or the composition of such a transformation with reflections in diameter. So again, it's hard to interpret because we don't actually recognize the wordings that are in the theorem. So let's break it down in a simple words. So it actually means that uh, isometries is just like how hyperbolic moves inside the Poincare disk model. These are the allowed ways to move things around it, without changing their shapes or their size. So either way, the formula looks pretty scary, I think, but it's actually just saying two things. We have the quantity of z minus a multiplied by the quantity of 1 minus a sub z is where we slide things inside the desk. We move, let's have, this is point Curtis. We move, let's have a star. We move here, we move there, and we move there. It's like the things how we slide inside the point of the desk. And we have the e to the power of 10, or e to the power of I theta is equals how they rotate inside the point of this model. So again, if we have here uh, a hyperbolic triangle, if we rotate that, it's going to actually look like this. If we move that here, then that's going to be look it's going to looking like this. So that's how it's simply the simplest understood of isometries in the Poincare disk model of the theorem. So you can slide the hyperbolic around, you can spin them, you can rotate them, you can flip them over. So that's the third theorem of Poincare disk model. Now So let's move on to theorem 4. We have the geodesics arc orthogonal arcs, where the statements clarifies that the hyperbolic lines, geodesics, in the point geodesics are precisely the diameters and circular arcs that intersect the boundary at right angles. First, let's derive the terms that we use because it's actually pretty hard to understand if we actually don't know what these words means. So first, let's what is geodesics means. So geodesics are the straightest possible lines or possible paths in any kinds of space. So in flat surfaces, we have straight lines. Uh, on Earth's surface, we have the great circle, or what we call the equator, and when dealing in the hyperbolic space, we have special arcs in the Poincaré-Desk model. So, why are geodesics called orthogonal arcs? Again, first let's derive the variables. Orthogonal arcs means lines that meet at 90 degrees angles. So, lines that meets at 90 degrees angles. Now, geodesics is called are uh, are called orthogonal arcs because uh, they are forming the straightest paths possible by hitting the boundary at a right angle, at a 90 degrees right angle. Makes them the uh, shortest path possible in this warp space, in the hyperbolic space. Now, just like drawing here, to get um, to get to the boundary of of from the center, you can actually use a path that actually uh, like that. So we are going to have to make a orthogonal arc which will form a 90 degrees right angle of the boundary. So that is a 90 degrees right angle because it creates this 90 degree if you face right here, right? So the boundary circle, the boundaries of a circle is infinity. We know that already. So when you travel in the hyperbolic space, you want to go in through a uh, straight line without veering toward infinity. Uh, infinity. Because actually, in this flat surface right here, because I can show you, because we are not in the curved space, it actually looks like this. Using the orthogonal arcs, we can. Sorry about that. Uh, Using the orthogonal arcs, we can actually see that boundary using like this. This is the boundary right there, right here. But actually, the boundary is here. It's infinitely stretching because it's a curved space. So to uh, to make the shortest possible path, we make a straightest line possible without veering toward infinity. So that's why to get to the boundary right here, we can actually use the geodesics to form geodesics that uses orthogonal arcs to make to go directly from one point to another without getting pulled toward the edge of the boundaries. So, real life example. So again, we already know what it looks like. This is America right here. So if this is Philippines right here, if we the short to make the shortest path, we make again the geodesic the fastest path or the straightest path possible. So it's going to be a 90 degrees orthogonal arc right there. But actually, the earth is actually curved, so meaning it's actually like this. What I'm saying is that The fastest route is actually the straightest line of what we see. So uh, uh, that's what is discussed in the theorem for, which is why we call the geodesics, or what we call the straight lines possible, are called orthogonal arcs, because they attack, or they point to the boundaries using 90 degrees at a right angle. So now we are in the horocycle characterization of Smart 1998. So in his statement, a holocycle in the Poincaré disk is a Euclidean circle tangent internally to the boundary circle, and it is orthogonal to the pencil of asymptotic parallels. Now, the wording side there is actually hard to understand, but again, it is simply as this. There is a point of infinity, or a point of boundary, at some point on the boundary. So I don't think that you get that explanation, but let's just draw it to understand. So in the Poincaré model, this part here is what we call the boundary, right? The infinite boundary. Now, as you move closer to that boundary, the boundary will keep expanding. So meaning, at some point, the boundary's point is right here. Now, when you get there, that is what we call the holocycle. A point of boundary at some point in the Poincaré model. So that is the explanation of what is a holocycle. Now, moving on to topic 4, the hyperbolic trigonometry in Greenberg and Ryan. So I'm just going to read this because it's actually existence enough. So for a hyperbolic geometry triangle with sides A, B, and C of opposites angles ABC, cos HC is equals cos HA cos HB minus sin HA multiplied to sin HB cos C. While the hyperbolic law of sines is sin HA all over sin A is equal sin HB all over sin B is equal sin HC all over sin C. Now, I think that concludes the report of hyperbolic geometry, the theorems based on the reference, and uh, mathematicians that work together to explain the hyperbolic space and hyperbolic space. And that is all. That is all of our topic for today. So thank you again for um, giving your time to listen to this topic. So I hope you understand. I hope you understand quite a bit, and I look forward in teaching this topic again and again after some time. I will be mastering it, so you can actually understand it further. So again, thank you for watching. So goodbye.